Molecular geometry. This is a two-part lesson. We're going to go ahead and do a rapid review of what we covered yesterday. Actually, we started with a review of polyatomic ions, so I'm going to go ahead now and just rapidly go through that whole section real quickly, and just to refresh your memory, since it is this module and it is new. When we talk about ions in the past, ionic bonds, we had sodium and chlorine as our example. Sodium has one valence shell electron and chlorine has 7. We said before that sodium would rather get rid of 1 and chlorine is looking for 1 to complete its octet. And so when sodium donates that electron to chlorine, it now becomes chlorines. It becomes now chlorides electron, and it comes with a net positive charge to the sodium and a net negative charge to the chlorine, and those two opposite charges attract one another, and so an ionic bond is formed, and an ionic molecule is formed from that bond when the positive and negative ions attract to one another. For polyatomic ions, first one we talked about is the hydroxide ion. Hydrogen has 1 valence electron, oxygen has 6. They actually form a covalent bond between those two. The resulting ion over here, see it has 1 valence available, 1 valence location. Let's go ahead and use sodium as an example again, and if sodium were to donate so that this octet could be full, the resulting ions are the sodium ion and the hydroxide ion. It has a negative charge. If we were to go through and count, we would see that there are 6 protons, and 1 proton makes 7 protons, but there are 2, 4, 6, 8 electrons. And because there's 1 more electron than protons, it has a net negative 1 charge. Now, in this instance, sodium has the positive 1 charge, and just like before, they come together and form an ionic bond. It's an ionic molecule with a polyatomic ion. Polyatomics are multiple atoms that are bound together with a covalent bond and yet have a net charge, meaning they act like an ion. Okay? This is double review, so I know I'm going fast, but we've already covered this. Metals and polyatomic ions, a positive metal, or here, if a polyatomic ion has a negative 2 charge or 2 negative, it would take 2 single positives to neutralize and get a molecule that has a net 0 charge. So it's no longer reactive ionically. Part of the reason I'm going through this is we're also going to be having a quiz soon on the polyatomic ions, which I promised you a couple days ago. That chart, which we'll see here in a minute in review, you'll be given some names and have to provide the formula. You'll be given some formulas and have to provide the names. In this case, our ammonium, it's our single exception to the rule. Ammonium is a positive ion, so it's going to bond with something that has a negative charge. It's going to bond with an anion. It acts as a cation. Here's our list of polyatomic ions. This is table 5.1 for 3rd edition, table 9.1 for 2nd edition. It lists all of the polyatomic ions that you're responsible to memorize and their formulas and their charges, because knowing the formula and knowing the charge is going to be very significant in figuring out the formulas for the compounds. A couple of the hints we had, the 8s and the ites. Whenever you have an 8 or an ite in the name, it means it has an oxygen in it, which the vast majority of them do. I know hydroxide has an oxygen in it, but if it's an 8 or an ite, it has a oxygen in it. And then these 3 different pairs, part of the ones you're responsible to know, that whenever it has an 8 in it, it has more oxygens than the ite. So chlorate, chlorite, the 8 would have 3, the ite would have 2. So if you remember, the chlorate and a chlorite is a ClO molecule of some kind. One of them is probably a 2, then the other one is a 3. Which one is it? The one with the higher number is the 8. The one with the lower number is the ite. Let me go ahead now. I mean, that's a quick review of the polyatomics. I don't want to spend all of our time on that. I'm going to go forward to what we covered yesterday with VSEPR. This is the part we really want to make sure we review, because we're building today's lesson off of this or reviewing with this. VSEPR theory, we talked about, started with the idea that what we're doing is going from a 2-dimensional model to a 3-dimensional model, okay? We're taking something here that's represented in 2-dimensional space, and we're now going to try to represent it in 3-dimensional space, because real life is in 3 dimensions, not 2 dimensions. VSEPR theory, and I drew it here as indicating the atoms themselves, the hydrogens. What's really happened here is remember, this stands for valence shell electron pair repulsion. So we're looking at the electrons in the valence shell, and here there are 8 in the carbon valence. We're looking at the center atom, the center molecule, in this case, the center of carbon, excuse me. And I sometimes refer to that as the hinge element. Carbon here is the hinge, and everything else is a arm outside of that hinge element of carbon. 4 hydrogens in this case, and it's actually the electron pairs that are repulsing one another. They're repelling one another. Here we've got 4 sets of 2. As we talked about yesterday, that these acts of repulsion, as they're repelling one another away from each other, they're all exerting the same amount of force. And as all of these 4 are exerting the same amount of force away from each other, they're trying to get as far apart from one another as possible. The geometry that represents that in 2 dimensions is a 90-degree angle. Because if any one of these hydrogens moves, yes, it gets farther away from one hydrogen, but it gets closer to another one. And so the point of perfect symmetry of balanced force in 2 dimensions is going to be 90 degrees. So if we had an 89 here, it would be 91 here. Well, 89 would push back and form 90. They're all going to like kind of spring to a 90-degree offset from one another. Now that's in 2 dimensions. As we said, however, real world is not 2-dimensional. Real world is 3-dimensional. So let me go over here again and get the manipulatives for us. We're going to hand these out one more time. I know I'm doing a quick review, but we had a couple students that weren't here yesterday. I want to make sure that we cover this for them at least once together. Pass those straight back. All right, so what we did yesterday, just to refresh your memory, is that what you have in your hand now is going to represent the molecule that we're about to build. And what I've started over here is this is the beginning part of drawing how to represent this shape in 3 dimensions. This represents this molecule, this methane, the CH4, with a central carbon and 4 hydrogens bonded to that central atom, equal distant apart. And you see that doesn't look like this, right? It's not a flat molecule. It's showing it in 3 dimensions. Because what happens in 2 dimensions, this is the best way we can represent it, but when we go to 3 dimensions, the way it really looks, that the greatest distance that it can move in 3 dimensions is not 90 degrees, but it's actually 109 degrees. So let me draw this shape up here and we'll go through what it means. The distance, or the angular difference between these bond angles, these bonds, this angle is 109 degrees. At 108 degrees, it's too close to one and too far from another, and they'll push back again. They'll spring and go to exactly 109 degrees, because 109 degrees is the distance that every point can be from the greatest angle, or the angle of symmetry between all of these different angles is 109 degrees. Every angle that you look at on this manipulative, every angle between these bonds is 109 degrees. This is a perfect symmetry in 3 dimensions, 109 degrees. Now, if you were to take the manipulative, turn it so that you use your hand to represent, let's say, the board. It's the plane that we're drawing it in. What you see over here, these 2 hydrogens with the solid lines, they represent the 2 bonds, if you were to lay your hand like this, into the plane of the board. So this hydrogen are represented here by these 2 legs on the right-hand side in the plane of the board. But you'll notice, as you look at it, you've got one leg of that tetrahedral that goes backwards into the board, and you've got one leg that comes forward out of the board. And that's why we use these symbols here of dotted line and this long triangular shape to represent this bond is the bond that is back into the board, and this shape here represents this bond coming out from the board. But the angle between every one of these, any way you could orient it, between bonds is 109 degrees in all cases. Okay, and that's the tetrahedral. This is our 4 points of connection symmetry. You can modify that some by going to the next model, or the next shape we're going to talk about, the pyramidal. If you take your manipulative, remove one of the bonds, the bond that's holding this hydrogen, and now have reduced it down to an NH3 molecule. What you have is a shape that's still based upon the tetrahedral, but with one minor difference. Now we've lost the bond on the top, and that bond, losing that bond, is based upon the fact that nitrogen had 5 valence shell electrons and now has an unbonded pair. That unbonded pair on your manipulative, you could think of it as that little piece that's sticking out of the top. That may represent an unbonded pair. Now remember, it's not the repulsion or repelling of the atoms, it's the repelling of the electron pairs. And so there still is a force of repulsion up here from this electron pair. As a matter of fact, what did we say in class yesterday? How does this force compare to a bonded pair? It's greater. Good. It's greater. This bonded pair basically stays close to home and has a greater effect of pushing the others away than a bonded pair would. So if we had a bonded hydrogen up here, if we did, which we wouldn't with a nitrogen in the center, but if we had a shape that was based upon 4, the angle would be 109 degrees. But now that we have an unbonded pair on the top here and it's pushing down even harder, what it's going to do is cause these other 3 to press in. And what example did I use from our classroom when I described what this looks like? Do you remember? The tripod that's holding the camera. That's why it's called this pyramidal. If you think of the tripod with the camera on top, that might look more like a tetrahedral right now, but if the camera were down close to the top of the tripod, where the actual 3 legs come together, it would look like 3 legs of a tripod with a camera sitting on top of it. Okay, and that's how I remember what this shape looks like, this pyramidal. It's not a tetrahedral, it's a pyramidal. It has, if you were to draw out from point to point to point, and the peak, it looks like a pyramid sitting right there. And the angle, because the electron pair here pushes down more than a bonded pair would, is 107 degrees. Now that 107 degrees is between all of these bonds. Okay? So every bonded leg between them and another one has a 107 degree angle. The angle between the unbonded pair and these legs would be greater than 109 degrees. But we're concerned about what is the bond angle. So the bond angle here is 107 in a pyramidal model. Going to 2. We're no longer having a geometry that's based upon a tetrahedron. Okay? So this doesn't apply anymore. This is really just going to be used for your tetrahedral and your pyramidal. Now we're looking at a molecule which has 2 bonds coming out of it. So look at the pivot element. It has 2 bonds and 2 unbonded pairs. Now what did I say happens when you have an unbonded pair relative to a bonded pair? The unbonded pair exerts more force. So what do you think happens when you have 2 unbonded pairs? They're providing even more force, repelling the bonded pairs. And so whereas the angle for 4 connecting points was 109, and the angle for 3 connected points with an unbonded pair was 107, the angle with 2 connections and 2 unbonded pairs is 105. So notice in all 3 of those shapes that if you looked at your pivot atom, they would have 4 points around them. They would have at least, in the tetrahedral, 4 bonds. In the pyramidal, 3 bonds and an unbonded pair. In this one, which is the bent molecule, this is how we represent water, we have 2 connections and 2 unbonded pairs for an angle of 105 degrees. Now in this, let me go back to this one more time. In this diagram here, this is still 3-dimensional. What you notice though is that we're able to draw these 2 bonds in the plane of the board, and these 2 unbonded pairs we're just representing in those locations. They're actually offset. They're not, perfectly flat in the board. One of these unbonded pairs would be kind of forward a little bit, one of them would be kind of back a little bit. That's not the point of the lesson here. The lesson is to determine what is the shape and what is the angle between the bonds. So the angle between the bonds and the unbonded pairs is not at issue right now. When we go to the trigonal model, for everyone we've done up to this point, there have been 4 things around the central atom, the central pivot atom. There have been 4. When we do a Lewis structure in 2 dimensions and we notice that there are only 3, if there had been an unbonded pair here, we would be back to 4, and it would be one of those 3 shapes we've already covered. But in this case, there are only 3 attachments to the pivot atom. 2 hydrogens and an oxygen in this case. And I said we're going to treat a double bond. We recognize that the double bond contains 2 bonded pairs, whereas each one of these only represent 1 bonded pairs. But when it comes to the geometry, we're just going to consider this a connection point. So there's 1 connection point, 2 connection points, 3 connection points. There are no unbonded pairs. And so what happens is the molecule can be represented with no bonds indicating a bond that goes backwards or a bond that comes forward. That's why this shape is a trigonal or triagonal. This triagonal shape is sometimes called a planar triagonal. Why? Because even though the oxygen, the hydrogen, the carbon, and the hydrogen over here are in 3 dimensions, and if you looked at them from the side, you would see width to them or depth to them, they can be represented on a 2-dimensional space simply like this because none of them are going to be forward of or back of the others. They're going to form in a plane. But because there are 3 of them, and they want to be equidistant apart, they want to push so that the angle between each bond is exactly the same. What is the bond angle? All the way around is 360, broken into 3 parts, and so each bond angle is 120 degrees. See? And finally, the linear. The linear is the most straightforward one. We said we can have a linear whenever we have 2 atoms that are bonded to each other with no pivot atom. So most common case to talk about is the homonuclear diatomics. In this case, chlorine. We have 2 chlorines that are sharing an electron. Each of them are sharing 1. So we have a shared pair here forming a covalent bond. There's no pivot, but they're bonded together, which means whenever you have 2 atoms that are bonded to each other to form a molecule, it's always going to be linear. But in the case where you have 3 elements bonded together, notice here there's only 1 connection point on each side. There's 2 connection points total to the pivot atom, the central atom. 2 connection points total. And because these 2 connected points want to be as far apart from each other as possible, they're at 180 degrees off of each other through the pivot atom. It's 180 degrees. If either one of these comes any closer, it's farther away this way, but it's closer this way, so it springs back. It's always going to form in a straight line, a linear molecule. And as I mentioned yesterday, you may see the Lewis structure like this. This looks just like a 2-dimensional Lewis structure, right? There's no difference. The way you can tell if this is written as a 3-dimensional VSEPR diagram is that you will actually see the electron pairs pushed away and put on the diagonal, because they're trying to represent the fact that this distance here, this angle between that pair, this angle here, and this angle here are approximately the same. They're not exactly the same, but they're approximately the same. But the key angle we're looking at here is not the angle between the unbonded pairs and the bonded pairs. What we're looking at is the angle between 1 connecting point and another connected point. In this case, again, 180 degrees. Mentioned in the book, diagram 5.2 or 9.2, depending upon your edition, is a summary table of all these things. They give an example of each one of the kinds of geometries. And notice here about the bonded pairs. When you draw your 2-dimensional Lewis structure, you can look down and look at this table and say, okay, I have how many bonded pairs? How many bonds do I see? Do I see 2 bonded pairs, 3 bonded pairs, 4 bonded pairs? And how many non-bonded pairs do I have? And so by looking at this table and comparing how many bonded pairs and how many unbonded pairs, you can see what shape is going to be. And if you know the shape it's going to be, that shape has a predetermined geometric angle. You know, what's the angle between the bonds? So the 5 different cases here are linear, trigonal, tetrahedral, pyramidal, and bent. I think this is where we left off yesterday through this example. What are the shape and bond angle of a PHCl2 molecule? We're going to determine the Lewis structure. We do that by saying, okay, this molecule has a hydrogen, a phosphorus and 2 chlorines in it. If we draw the two-dimensional Lewis structure, what is going to be the pivot atom? What's going to be the central atom in this structure? Phosphorus, because most open addresses, the most connecting points. It can receive the most connections. And so by our standards, we're going to put that and make it the center. Matter of fact, we're going to make it the center, and in order to, the way you get used to visualizing it is we can see that there are going to be 3 connecting points, and we'll put the unbonded, or the, excuse me, the unbonded pair to the top as we make our Lewis structure. So we're going to rotate it, put the unbonded pair on the top. We're going to place the other atoms that are part of that molecule around it and orient an open address or an unbonded electron, whichever way you look at it, towards our pivot element. I'm going to go through and move it up here. And then after we've done this, we can go through and say, okay, these electrons here are actually being shared. So we're going to represent those as covalent bonds by replacing the 2 dots by the solid line. So this is our 2-dimensional Lewis structure for that molecule. The next step is, okay, what do? I take the 2-dimensional and I look at it for my 3-dimensional. What is it going to look like in 3 dimensions? So in this case, how many items, this is maybe one way to look at it, I forget exactly the term they use in the book, but what is the number of connections or unbonded pairs that are around the central atom, around the pivot atom? There are 3 bonded pairs, but you also have 1 unbonded pair. So you have 4 considerations. You have to remember that this shape is going to be based on 4 different items. It's going to be based on then a tetrahedral. It's either going to be a tetrahedral or it's going to be based on a tetrahedral because it has 4 different points of connection around the central atom. It has 4 points, but it only has 3 bonds. Now, if you use the table, look over here, just so you're sure you can use the table. How many bonded pairs does it have? It has 3 bonded pairs. How many unbonded pairs does it have? It has 1. 3 and 1, it is a pyramidal. So if you just memorize that, if you just memorize, okay, 4 connections, it's 3 bonded and 1 unbonded, 3 and 1 unbonded, it's a pyramidal. But now let's go through and let's do the shape and reason this out. Okay. Put the phosphorus in the center, and because it's based on a tetrahedral, we're going to have the 1 behind and 1 forward, and 1 in the plane of the board. And go ahead and place those atomic symbols around it. Now, I didn't put all the dots around them. There wouldn't be any around hydrogen, but there would be around the chlorines. There'd be 6 dots around chlorine and 6 dots around this chlorine, but I didn't want to clutter it up too much. But you can see, based on this, and we're just looking really at the geometries around the pivot atom, that it's a pyramidal. It has 3 legs and a camera on the top, like the tripod. The shape is a pyramidal. So you can figure out the shape by using the logic of it would be a tetrahedron if it had it would be a perfect tetrahedral if it had a bonded pair, but it doesn't. It has an unbonded pair, which means it's going to take the angles and squish them down even farther. If it was a perfect tetrahedral, it would be 109 degrees, but since it's not, the unbonded pair squeezes them a little bit more. It actually is 107 degrees. All right, there are a couple more examples in the book, and I would encourage you to read through those. On 3rd edition, page 184, the Si2 molecule, I'm sure there's something comparable in the 2nd edition as well. Where are we time-wise? We've got about 15 minutes left in class. There's 2 different ways we can approach this. We can either, at this point, go through some of the on your own 5.4 through 5.8. We can do that together as a class. One thing I'd maybe prefer that we do is we're going to go ahead and watch Tyler DeWitt. Tyler is one of those video resources that I have that teaches this. He does a great job at it, and I think it's helpful for us sometimes to see someone else teach it, the same material again. And so I'd encourage you to go ahead and do the on your own, of course. Those are going to be quizzable material for you. But go ahead and do the on your own and check the answers. The answers for them are in the book. For those of you in second edition, if you want to look at the on your owns real quickly, third has something like this. Determine the shape and bond angle of an oxygen molecule. Okay. The eighth one, what are the shape and bond angle of an SiCl2O molecule? Okay. So both of, if these all deal with bond angles and shapes, go ahead and do your own, and we'll go through both the second and the third edition on your own briefly.